Alright, so I guess we'll get started since it's already 11:31 now. So today we're going to be doing the lecture for the 5th lab, which is kind of amazing. It's already getting to the 5th lab now. So we're going to be doing that today. It's a pretty fast lecture too. And I was thinking about this, you should enjoy this while you can, because the lab next semester being 306B, all of the lectures for that, and really all of the other labs, they're a lot longer than the lectures we have in this lab. So enjoy it while you can. And for your grades for the second memo and the third memo, as you can probably tell from Canvas, haven't done that yet, which I don't like. Usually I like to grade your memos within 1 week of your submission, because I know, if I'm in your place, I want to have my grade back within a week too. So I get that, and sorry it's not already graded. This week I've been busy with my own midterm project that's due today, but once I'm done with that, I'll be grading your second memo on the weekend, and it'll for sure be graded before your fourth memo is due. So remember, your fourth memo, that's due on next Friday. Okay, so your second memo for sure will be graded before that submission. Alright, so that's kind of it for the announcements, and once I'm done with the second memo, of course I'm going to grade the third too. But make sure that you're looking at the feedback on the first memo, because that'll be the most detailed, at least individualized feedback that I have. Okay. Alright, so first thing we're going to do, we'll take a look at what this lab is going to look like. So we don't have a little online procedure that's on VKS. So I just found a YouTube video. This is one that I found last semester. It's pretty good. So in this lab, Charpy Impact test. So what we have, we're going to have 3 different materials. So I think, the typical aluminum, and the 2 different steels that we've been using throughout the semester so far. And they're going to be these little notched bars that you see here. Alright, and each of these are going to be subjected to 6 different temperature environments that we'll talk about later, but it's going to range from cold to hot. And you're going to take it out of that temperature environment, you're going to place it on this test stand, not using your hands like this guy. It's probably just a room temp sample here, but we're actually going to be using this kind of, tong to pick them up and then place them on the test bed here. And you're going to line it up as best you can in the center. And you can see the notch right there, by the way. So you're going to line it up in the center, and then you're going to run the test. So this guy's got a huge pendulum. Kind of sounds like a euphemism. So on the very front of the test setup, there's a big dial gauge. So here's a better look at it here. So there's a big dial gauge, and that's going to tell us the amount of energy that is absorbed by each specimen when it's fractured. Okay, and this guy, he has this little rotation to actually lift up the pendulum. We don't have that, so we got to lift it up ourselves. And I think it's 60 pounds, so it's pretty heavy. So if you're doing it by yourself, make sure you're using good form, don't want to throw it the back. But really, 2 of you should be lifting it up at the same time just to be safe. And of course, when we're doing this, got to make sure no one else is down here putting the sample there. So basically, we'll have you put the sample in first, and then you'll lift up the specimen, and then you can run the experiment. So when you, did I say lift up the specimen? I meant lift up the pendulum. And when you lift it up all the way, it can lock into place too. So it's a little safe that way. Alright, and then let's see if he shows a view from here. So we're all the way up top here. Ours doesn't go quite this high, but ours is maybe about here. So we have a good amount of potential energy. And then again, it locks into place, and you can release it. It'll swing down, strike whatever specimen is on the test bed, and then it's going to have it fail. Alright, let's see if they run it. So he's zeroing out this the dial gauge right there, and there it goes. Okay. You know, here there's nothing in the actual test bed right now, I believe, so it went back. It was at 0. Alright, so let's look at this one. I'm gonna kind of skip through the video. Okay, so he's putting it down there. You see, he has a tool to line it up perfectly in the center. We don't have that, so that's a source of error for the experiment, by the way. So you want to make sure you line it up in the center as best you can. Okay, zeroing that out. And you saw that it just showed up down here. It's broken into 2. And then there should be a picture to see what that looks like. Alright, so you see this one too. It didn't absorb that much energy. So that's what we're looking at in this lab. How much energy each of these absorbs on impact. So here, I think they're measuring in joules, but we're going to be measuring in foot-pound in the experiment. So this didn't absorb very much energy, so when we look at the fracture surface, you should see a very clean cut. And does he show it? Okay, here we go. Okay, so that's the specimen that he just broke. So again, it's a very clean cut here because, you know, we'll talk about this. This was a brittle failure that occurred, a brittle failure mode. And because of that, it's going to be clean cut because there's not much deformation that can occur in a brittle failure mode. Alright, and then there's one more to look at. And this material here, it's going to have a ductile failure. Okay, you see here, it absorbs quite a lot more energy here. And yeah, you could look at that surface. It's very jagged, very rough. It's not even completely broken into 2. And we can compare the 2 here. So on the left, that's the one they just tested. Really rough, not even broken into 2. And the one on the right is the brittle fracture. Okay, very clean cut. Alright, so that's what we're going to be doing. And we have a camera that's in the lab too. It's kind of a macro camera. So we can take pictures of the fracture surfaces right after the test. And you'll be doing that, and you're going to have it in your memo where you're going to have at least a few pictures that show the differences of a brittle fracture mode right here, ductile, and then something kind of in between. And you'll comment on that and discuss it in your memo. Okay. And yeah, okay. So let's go and start on the actual notes. So just a little preview for what it looks like. And I like this lab too, because it's more involved. So, you know, so far in the labs, they haven't been that involved for you guys, right? You've just really been pressing play. Yeah, you do some setup on your own, which is good, but a lot of the labs so far, you're just going in the software, pressing play, and sitting around and waiting, which is not the most fun. So this lab, it's really involved because you're doing everything yourself. You're gonna set it up yourself, run the experiment yourself, just because it's swinging down, and then you're gonna collect the data in your Excel sheet. Right. So to start out, we're gonna talk about the strain rate. So throughout the semester, when we've been pressing play in the software, we've also been setting up some initial test parameters, and one of those is the test speed. So that's the deformation rate, or really you can think about it, you know, if we convert to strain, we're setting the strain rate, but technically we're setting the deformation rate, and usually that was set at 0.01 inches per minute, so it's very slow. And either way, that deformation rate, if we convert it to the strain rate, it's a very slow strain rate. You know, for the first test, first 2 tests really, was over the course of several minutes. And the third test and the fourth test, you know, maybe not quite as long, but either way, the strain rate was pretty long, right? And in this experiment, it's going to be essentially instantaneous, or at least relatively instantaneous, because we have an impact. So instead of this fracture occurring over the course of minutes, it's going to occur, instantaneously, essentially. And from that very intense or fast strain rate, we're going to be looking at how much energy each of these specimens can absorb, and that's another way to just look at the toughness that they have. Okay, so that's kind of the difference for this lab. Okay, and then of course in this lab, we're going to have a very sudden load, so we're going to have a very high strain rate. Alright. Okay, and again, this is done, or let's first say this is called the Charpy Impact, right? And it's done via the pendulum that you saw. So we load that up to its highest point. There's a lot of potential energy. We let it go down, strike the specimen. That potential energy converted to kinetic energy. Some of that kinetic energy is taken away because you hit the specimen. Then the dial gauge, that's going to be able to directly measure how much energy was absorbed on that impact. And then we can measure the toughness of all of these different materials. And of course, we're doing this at a range of temperatures. So we're going to see how each of these materials behaves, or how tough they are, across that range of temperatures. Okay, so going on to toughness again, we'll talk about this a little bit more. Okay, so toughness is going to be the amount of energy that is absorbed. And for our experiment, it's an impact, so we're going to say impact toughness. Okay, and we can have a stress strain curve and we can calculate the toughness as well. So that wouldn't be really an impact toughness. In that case, that would be something for like a tension test that we did in the first two labs, but either way, it's still related, so I thought I would mention it, and it kind of gives you just a better kind of feel for toughness, I think. Okay, so we have a stress strain curve here. We have strain on the x-axis, stress on the y-axis. Okay, so we're going to have these three different materials, and to calculate toughness from a stress strain curve, all you have to do is calculate the area under the curve. Okay, and again, we're not doing this in this lab because we're doing an impact test, but again, this is still relevant because we're talking about toughness. It'll give you a better idea of what toughness really means. So again, toughness, amount of energy that is absorbed. If you have a stress strain curve, you can calculate that by looking at the area under the curve. So here we have 3 different materials. So the blue material here, it's really strong. Okay, it can handle quite a lot of stress, but it doesn't deform very much, so it's not very ductile. Okay, so we have a strong, kind of brittle material here. And if you calculate that area under the curve, it's not very large, so that's implying that this blue material has a very small toughness, or very little toughness. And same thing with the red material. So the red material here, it can't handle very much strain or stress at all, so it's pretty weak, but it can handle quite a lot of strain, so it can undergo a lot of deformation. So that might be something, I don't know, like rubber, something like that. I mean, if you really want to go insane, you could think about gum. You can stretch gum, right, quite a lot, but it's not that strong. And then for the blue one again, so very small toughness, that would be something like a ceramic material. Very strong, but also very brittle. Okay, and then our green material, it can handle a fair amount of strain and a fair amount of stress. So if you calculate that area under the curve, it's going to be very large compared to the other two. And so that's going to be, it has quite a lot of toughness. Alright. And so again, while we're not doing a stress strain curve in this graph, it's still relevant because, I want everyone to realize that the strength of the material isn't, and the deformation isn't necessarily related to the toughness. We're looking at the area under the curve here to see how tough it is. But for this lab, even though we can have a very strong material or even a very ductile material, the toughness can be different. So really what we're going to see is, and this is going to change too, more importantly, depending on the temperature for some materials. So I'm kind of getting a bit ahead of myself here, but you'll see later on, we're going to go over how we'll see aluminum. That's going to be very tough throughout all the different temperatures that we're going to have. And then something like steel, that's only going to be tough at certain temperatures, more high temperatures. And it's not going to be tough at all at very low temperatures. But again, that's what we're going to talk about a bit later on in this lecture. Okay, so we know, in just like everyday life, we know what a brittle material is and a ductile material, but in everyday life, we're kind of in room temperature or something, around there. We're not in these kind of extreme environments typically. It's not like we're chilling out in an oven or something, or chilling out in, I don't know, in liquid nitrogen. So very extreme. So we're not doing that, right? But we know what a brittle material is, like maybe glass. So my iPad screen, it's chipped in a few spots here. Or if you drop your phone and you break the glass screen, it shatters, right? It's strong, but it's not very ductile at all, so it's brittle. And then a ductile material, we already said it before, but something like gum, you can deform that quite a lot, but not very strong. So, we know that, and we have a good understanding of that, but what we really want to focus on in this experiment is not being as specific as that. We want to have a more general understanding of brittle versus ductile. More specifically, a brittle fracture and a ductile fracture, which is kind of what I said in the beginning of this class when we were looking at the video. So we saw a brittle failure, or a brittle fracture failure, and then a ductile fracture failure. So we want to start using those terms for this lab. Okay. So a ductile fracture mode, basically, it's still going to be the same kind of definition that we have for something that's ductile. It's going to mean that the specimen will deform a lot and then fracture. And same thing for a ductile fracture mode. There's going to be very little deformation, and then there's going to be failure. But the key takeaway here is that these fracture modes, a material can have varying fracture modes depending on the temperature. So at one temperature it might be ductile, another temperature might be brittle. Okay, let's write all that down. All right, so again, the key takeaway here that I want everyone to kind of focus on is that we want to use the term of fracture mode because a material, depending on the material and the temperature, it can behave differently. So we're going to have an example now. So big one would be the Titanic. Got that from Dr. James. So I'll show you some other pictures too. But basically, the Titanic, I think it was made of steel. So in kind of warm to hot environments, steel is good at being having a ductile fracture mode. So it's going to be a tough material. But at very cold temperatures, if you're in water with icebergs, it's going to be pretty cold in there. Steel starts to behave as a brittle material, meaning that it's going to have a brittle fracture mode. So, if they hit an iceberg, not necessarily really an impact there, just because it wasn't like an instantaneous kind of impact for the damage it caused. But either way, in these cold environments, steel is going to act as a brittle material, so it's not going to be as tough. And that's why the Titanic failed, right? And let's look at other pictures here that I just found before class. There's a whole little blog post this guy made on a lot of ships that are made of steel and that have split into two, because all of these steel ships, they were in cold water, and then they start to behave like a brittle material, and they literally doing nothing, just chilling out in the water. A lot of these split into two, and you can see that you have a very clean cut. So here's a really good picture on one of these. And let's see, there's some good ones in here. This one, kind of insane. A lot of them, they're kind of already in the water. So anyways, there's a lot of cases like this, at least for older ships, where they were made of steel and literally just chilling out in cold water. They split into two because they were behaving as a brittle material, which you see this guy too, he's talking about. So different temperatures, depending on the material, they can behave as either ductile or brittle. I think it's kind of cool. I mean, not that it's breaking, but kind of cool, behaves differently. Okay, so next thing we'll talk about is something called the ductile to brittle transition temperature, or DBTT. So I'll first just say the definition, then I'll write it out, and then I think you can get a better idea when I make a graph for this. Okay, because it's kind of a mouthful. So the definition for this is the temperature for which the impact energy is halfway between the impact energy at the highest temperature and the impact energy at the lowest temperature. Okay, so I'll say it one more time. The dBdt is the temperature for which the impact energy is halfway between the impact energy at the highest temperature and the impact energy at the lowest temperature. Okay. And speaking of this, just to kind of throw it out there, and hopefully everyone remembers this, when we're actually doing the experiment, it's even more important now. When you're getting your specimen in a very cold environment, so that'll be for liquid nitrogen, and that's the most extreme one, versus the highest temperature, which is going to be from an oven. It's even more important that you quickly take it from that environment, put it on a test bed, and start it as fast yet, of course, as safe as you can do it. Because if you leave it chilling out for a while and it's either warming up or, in the case of the oven, cooling down, you're impacting your results. So you're changing what the result should be, and that's gonna mess with your dBdt calculation that we're gonna get here. Let's say you did a good job with the oven and you got that tested pretty fast, but you didn't do a good job testing the one at the liquid nitrogen test very fast. So then you're going to have, basically, it's not going to be as cold. Let's say that we're testing steel. It's not going to be as cold as it should be for liquid nitrogen, and it's going to absorb more energy than it should. So those two different kind of extremes for high and cold, it's not going to be as good as it should be, and that's going to change the ductile to brittle transition temp that you calculate in the end. So that's something to think about. That's going to impact your results there. So you really want to do as good of a job to test it as fast as you can, yet of course as safe as you can do it. Okay, so that's the kind of text definition, but again, I think it's a little more clear to understand this if we have a graph. So we're going to be making these graphs too on the memo. So on the x-axis we have temperature, and then on the y-axis we have the energy absorbed. So energy absorbed on impact. Okay, and then for steel specifically, and I'm kind of exaggerating the graph here, but you're going to get a graph that looks similar to this. So a nice little S-curve. I think of snakes every time I see this. So you'll see for steel at very high temperatures, it's going to behave as a ductile fracture mode. So it's going to absorb a lot of energy. It's going to be pretty tough in this case. But as we go down, the temperature goes down. It's not going to absorb very much energy at all. So it's going to behave like a brittle material. It's not going to be very tough. Okay, so we have the two kind of ends of the spectrum here. But from this very sharp S-curve that we have, there's going to be this, it's a pretty clear, well-defined transition temperature. If we were even more drastic here. you can see that the transition temperature is right there. We're going from a brittle material to a ductile material. So when we're actually calculating this in the lab, basically what you're, even saying calculating is maybe not the best term, but to do this, we'll look at the impact energy at the highest temperature. So that's going to be right here in red. Okay, and then the impact energy for the lowest temperature down here in blue. So we got those, and again, that's why I just mentioned that we want to do this as fast and safe as we can, because let's say we messed up the liquid nitrogen one down here, and it kind of warmed up a bit, then that point would be right there instead, and that's going to alter that transition temperature. Okay, so we have the two of them right there, and then what we have to do is look at the impact energy that is halfway between these. So let's say that's there, and then we can draw a line, or really in MATLAB we can use the poly x, poly y, I believe that's the function, to find our intersection point here. Okay, we'll see that's right there, and then we'll go on down, and then we can find our temperature, which we already kind of drew out here for the transition temperature. So that's representing when we're transitioning from a ductile fracture mode to a brittle fracture mode. And really this only makes sense to do it for materials that are transitioning from ductile to brittle. So that would be like for steel. But you'll see in the lab when we have aluminum, that technically doesn't even have a transition temperature, because it's actually going to be pretty tough throughout. So it's going to be staying pretty high up here on the graph for the energy that's absorbed. So we'll have that graph soon too. Okay, so there you go. That's the transition temperature. And again, not all of the materials that we're going to be testing are going to have this well-defined kind of S-curve here, like aluminum, and some other steels too, or that's all we're going to be testing is steel and aluminum. But other materials too, they might maybe they look something like that, almost like a stress strain curve. So again, not all of them are going to be as defined, and when they're not, we're going to have a combination of it being maybe a little bit ductile and a little bit brittle. It would depend on the material. And also, when that happens too, for those when it's not as well defined as this S-curve here, right around that transition temperature, you're going to see, even in this case too. So this would be like at room temp maybe, and that's going to be a kind of a combo of ductile and brittle. So it's not going to be a smooth cut, but it's also not going to be extremely rough either. Okay, and then of course, now this is just for, your own information. Ideally, we want to have that transition temperature for our material to be really low, because typically we're not in these very, very cold environments. And even if we are, we want to make sure that that transition temperature is as low as we can get it. So, if we're in the Antarctic Ocean or something, obviously it's going to be very cold in there. We want that transition temperature to be as low as we can possibly get it. And of course, you want to choose the right material for the job. So, not steel, at least not steel for the main bulk of the ship. You want to choose your materials smartly so you don't fracture in half. All right. And then of course you're kind of along the same lines, the surface temperature that you want to be at, it should be above that. So if you're in the Antarctic Ocean, you better be operating above that transition temperature. Okay, so last kind of thing we're going to be talking about here is the material structure. So the actual kind of crystalline structure of these materials that we're going to be testing. And so this is going to give us insight on how a material should behave for this curve that we have. So there's a class on campus actually for like just talking about material structure. I don't know what it's called. It might be called that. I don't know. So I've had students in the past that have taken it. I don't think it's a very popular class. I think it's a tech elective. So I've never taken it, so I don't know very much about material structure, to be honest. I pretty much know nothing about it. But we're not going to focus on this part in the lab, but it is another kind of thing that's just good to know. So for, again, the actual kind of crystalline structure of these materials, you can get insight, or you can kind of estimate how that material is going to behave for a range of temperatures. All right, so the first one we're going to talk about is a face-centered cubic material. So that'll be something like copper or like aluminum. So, for us, we're using aluminum in the lab. Okay. So for this, there's going to be very small decrease in toughness as the temperature is decreased. So these materials, they're going to be good to use in these low temperature environments because that toughness, even when we're getting colder and colder, it's not going to go down too much. So I'm going to draw a graph for all of these materials too, so we can get a kind of a preview of what we should see in the lab. So again, this will be something like copper or aluminum. Of course, you're not going to make your ship out of copper. Pretty expensive. Okay, next one is called body-centered cubic. Okay, or BCC. Okay, and for this, there's going to be that kind of very sharp transition from ductile to brittle. So what we drew here, this was like some kind of steel. That's going to have a very sharp transition from ductile to brittle. Yeah, so these ones, they're going to be pretty brittle at low temperatures, just like you saw in the graph here. Okay, and for this, an example material is going to be steel, like we talked about. Okay, so let's show this on, I guess we'll just show it on the same graph here. So what we've already drawn is, not FCC, sorry, that should say B. So here we've already drawn a BCC material, so something like steel. Okay, so there's very sharp transition from ductile up top for these high temperatures to brittle at the low temperatures. But we can also have a face-centered cubic structure like aluminum. Actually, I will do a new graph because typically what you'll see is the face-centered cubic materials, they're actually even more tough than the body-centered cubic at high temperatures, just by a little bit. So let me just do a new graph. Okay, so in red here we have our body centered cubic structure like steel. And then in blue, I'll have our face centered cubic, and that'll be like aluminum. Okay, so these kind of graphs that I drew here, they might be exaggerated from what you're going to see in the actual experiment. But yeah, you can see that steel, it's most definitely going to have a transition temperature. So it's at cold temperatures, it's it's going to be ductile it's going to be brittle. And you should see that in the experiment. So you should see steel at low temperatures, it's not going to absorb very much energy, and it's going to have a very clean fracture. So it's going to be very brittle. But once we go up to high temperatures with steel, it's gonna deform quite a lot, and it's not even gonna break in half, just like you saw in the video in the beginning. It's gonna absorb a lot of energy, and it's gonna be really tough. And then aluminum, I can't remember the exact numbers or not. I can't remember if it was above or below steel at high temperatures for our experiment. But aluminum, it's going to be tough throughout. So even for liquid nitrogen, it's kind of crazy. Even for liquid nitrogen, it's still going to be pretty tough. It's only going to decrease a little bit from its toughness when it's in an oven. Okay, so you'll see something like that. And that's what we're going to have for our graphs. And there is another kind of line we could have here, but we're not going to see it in our experiment, so I'm not going to draw it. But for that, it would be high strength alloys. And basically throughout the entire range, I guess I might as well draw it. For the entire range for high strength alloys, they're kind of chilling down here. So they're not very tough at all throughout this entire range of temperatures. Alright, but again, we're not going to be looking at that for this experiment because we're not testing those, okay? So we're going to be looking at aluminum and steel. Okay, and then another thing to kind of go over here is the temperatures, the range of temperatures that we're going to have in the lab. So we're going to have 6 of them, so it's going to be going from cold to hot. It's going to be liquid nitrogen to dry ice to wet ice to room temperature to boiling water, and then in an oven. Alright, so that's the range of temperatures that we're going to have. So we'll have little data markers on our graph because, right now these curves are implying that we have a lot of data points. We're only going to have 6, so we need to show the data markers on the graph. Okay, so that's it for this lecture. So, kind of fast, at least compared to the column. And yeah, so we're going to be doing this experiment in person next week. So be prepared for that. It's a lot more involved compared to the past labs. Also, be sure that you're on time. Most people, typically are, but for this one, it's only 2 groups this time because we only have 2 setups, and we only have, so much dry ice and liquid nitrogen, so we're only going to have 2 groups for this upcoming lab. Alright, so make sure that you're on time. Alright, so that's it for today's lecture. So if you have any questions, I'll stick around. Make sure that you turn in your 4th memo next Friday, and I'm going to grade your 2nd memos before that due date to give you more feedback. Alright, so that's all I got for today. So I'll see you guys next week, and have a good weekend.
Hey, I got a question for you. Can you go back? Because I missed something that you wrote down for the fracture modes. Can you go back real
Okay,
quick, just to make
yeah.
sure? Okay. Give me 1 second here.
Okay, yeah, you're good. Yep, see you guys. Have a good weekend.
Hey Patrick,
Hey,
for the memo 4, if our group is I believe we're still missing the peak load. Do we just grab that from another group or something? Or we asked already in the chat, but I don't know if anybody, I don't know if they're on here.
Uh, you were part of the pin fix group, right?
Correct.
Okay, yeah, so that's up to you guys. You guys gotta write down that peak load.
Okay.
Yeah.
All right. We'll figure it out. Thank you.
Okay, yeah, I think if you haven't already written it down, you can just look at the text file and you'll just kind of have to scroll through and find the max load.
Okay, cool.
Yeah.
Awesome. Thanks, Patrick. I'm all good now.
Okay, cool.
Have a good weekend.
All right, you too.